if I am going to have this gate, right, AC plus BD, you are going to get, like, you are going to represent in the form of AND OR representation. AND OR representation. As AND OR representation, you are going to get circuit like this. Okay. Can we represent the same circuit with the help of NAND gate? With the help of NAND gate? That is what my question. Yes, we can do, right? So if you are going to do like that, try to observe. For AND gate representation, how many NAND gates are required? How many NAND gates are required? Two NAND gates are required. So two NAND gates are required, right? In order to represent one AND gate, two NAND gates are required. In order to represent this AND gate, how many AND gates are required? Two NAND gates are required. In order to represent one OR gate, one OR gate, how many NAND gates are required? Three NAND gates are required. So total of 2 plus 2 plus 3, 7 NAND gates are required in order to represent the AC plus BD expression or the function, right? This is the general procedure. But the thing is, if your data is available in the form of sum of products form, the simple solution is, see, I will try to do. The simple solution is, try to take out the same structure. You are going to have AC, you are going to have BD. It will look like this, right? Now try to observe. So this procedure is correct, perfectly fine. But thing is, can we able to reduce with less than 7 NAND gates? See, maximum 7 NAND gates are required. This is maximum. But is there any solution to get less than 7 NAND gates? That is my question, right? Yes. Right. Try to observe. I am trying to make here complement. I am trying to put here complement, and I am trying to put here complement. See guys, if I am trying to put complement here and I am trying to put complement here, is there any problem? Again cancel, right? If I am trying to put complement here and trying to put complement here, is there any problem? Again cancel, right? Yes. Now if you look into this particular syntax, this particular thing, what is the meaning of this one? Try to observe. If I am going to have two inputs, x and y, if I made like this, meaning is this is x complement plus y complement. So the input is x complement plus y complement. X complement plus y complement, according to De Morgan's law, you can do like xy whole complement. Can I write? Yes, xy whole complement, right? The same structure I will redraw like this. AC, its complement, and BD, its complement, and I will try to redraw in terms of this dotted notation representation as, observe, x y complement. Xy complement was again as one NAND gate. You are going to get again AC plus BD, right? So this particular representation is equivalent to this particular representation. Right? But here we require to represent OR and AND gates. Here we completely defined in terms of NAND gate. So what I did in order to convert any AND OR representation into NAND-NAND representation. So this is what I can call it as NAND-NAND realization. So in order to convert AND OR gate to NAND-NAND relation, the simple solution is, you can simply put AND gates output with the complement and OR gates output with the complement and OR gates inputs with the complement, and try to replace the OR with the complements as NAND gate. That is simple procedure you have to do. But the thing is, if you would like to represent anything in the form of NAND gates, compulsory it should be in the form of AND OR representation, and if you would like to represent in the form of AND OR representation, compulsory it should be in the form of sum of products. This is the reason in the last class I have discussed the concepts of sum of products and products of sums. Okay, now try to debug this. Is it going to produce the same output? If you are going to give 0011 as input, you have to produce, I think, output 1, right? So 0 and 0 on NAND gate. So I think 0 and 0 is 0, complement is 1. So you are going to get 1 as output, 1 and 1 as 0, 0 complement is, sorry, 1 and 1 as 1, 1 complement is 0, 0. And this 1 will comes here, 0 will comes here, 1 and 0 is 0, 0 complement is 1, right? 1, 1. Both the circuits are same. But the thing is, industry having the advantage, they can able to produce only NAND gates. See here, in this particular representation, we have maximum number of 7 NAND gates. Here, this particular representation, we require 3 gates. This is the best circuit. Similarly, if you are going to have any expression in the form of product of sums, so that I can able to represent in the form of OR and circuit representation, right? This is what OR gates and this is what AND gate circuit representation. When you got this thing, you have to simply do the same process. At the outputs of OR gates, make the complements, and as you put the complement here, if you are going to put complement at the input of AND gate, they are going to be cancelled out. If you are going to put here also, they are going to be cancelled out, right? Now this particular representation I can be represented in the form of again XNOR gate, right? See, it will look like this, right? So this is x, y. What I can say, this is x bar into y bar. X bar into y bar I can write it as x plus y whole bar. X plus y whole bar means what? This is XNOR, which is equivalent to XNOR. Observe, which is equivalent to XNOR. So I can represent this entire circuit as like this: AC, BD, that's it. So this is the parallel or equivalent representation of this one. So this is what I can call it as NOR-NOR realization. NOR-NOR realization, right? So it is easy for us to implement any circuit with help of in terms of NOR-NOR relation when your circuit will be in the form of OR and representation, meaning that it should be in the form of product of sums. Product of sums, right? Basically, guys, here also, in order to represent one OR gate in XOR representation, one OR gate in XOR representation, you require 3 XOR gates. You require 3 XOR gates. Am I right? I think you require only 2 more. OR gate. OR gate requires 2 XOR gates. So 2 XOR gates. This OR gate requires 2 XOR gates, and AND gate requires, so total maximum of 7 NOR gates are required. Maximum of 7 NOR gates are required. But if you are able to follow certain procedure, you are going to get maximum of 3 NOR gates. So if you would like to convert the same thing, OR and gate circuit into NOR-NOR circuit, you can simply bubble up the outputs of OR gates and bubble up the inputs of AND gate. That's it.